in the third version of our swap array function, we are going to try something radically different. Okay, we are trying to pretty much implement a fast swap array. The motivation for this approach is that every time you call swap array with A1 and A2, what you put on the stack is the address at which A1 starts and the address at which A2 starts. Okay, and then we go through this loop, which forces us to iterate over every element of each array and swap them one by one. Well, the idea is, since we are manipulating addresses at which those arrays start, wouldn't it be better and more efficient if instead of swapping the contents of the array, I was swapping the addresses at which they start? Therefore, what I would like to be able to do is I pass A1 and A2 to my function, and the function is going to make it so that A2 now represents the start of the array A1, and A1 represents the start of the array A2. Why is it so much more efficient to do so? Well, if you have an array of 3 elements, it's probably not a big deal. If you have an array of millions and millions of elements, you will have to iterate over each of those. Okay, in the first version. In the second version, no matter what the size of your array is, you will try to swap them in the same time. Just a matter of assigning an address to two different variables. Okay, so in terms of algorithm complexity, you're going to discuss that in your data structure course. This is the difference between the linear algorithm. The more elements in my array, the more time it takes me to iterate over them. Okay, it takes me a linear time in the number of elements in the array. Now, the second version we're working on right now is constant. No matter what the size of the array is, I try to just swap around two addresses and I'm done with the job. No matter, once again, how many elements are in the arrays. So this is a general idea of what we are trying to do. Now, how are we going to try to implement it? This is swap array version 3a. You are going to see that we'll have two different versions of this function in this third step. I chose that my parameter would be expressed as int star p1, int star p2. After all, I'm talking about manipulating array addresses, so I might as well use my parameter indicated as arrays pointer on int and pointer on int. So when I pass a1 and a2 as effective parameters to this call, I'm going to pass the address of the first element of a1, the address of the first element of a2, and these are going to be stored in p1, p2. The body of my function, a pointer tmp on int, temporary variable. I assign p1 to tmp, I assign p2 to p1, thus overwriting the current content of p1. Then I assign tmp to p2, thus assigning the original value of p1 to the pointer p2. So what I'm really doing here is I'm swapping around those two addresses. Let's implement this function, test it, and see how it's working. And then our first question will be like, of course, why does it work? Does it work? And once we're capable to answer that, we're going to look in more detail at the stack diagram to understand exactly why it is working or not working. So this is a code. Let me remove this int hanover declaration, which we saw doesn't work. Let me move the exit now, so that we exit this code only after swapping with swap array version 3a. So that would be here. Save the file. We are going to compile and execute. So no compilation problem. A.out, execute it. Initial content of the array. Swap with 1. That worked. Swap with 2. That worked. We already covered that. Swap with 3. You can see that there is no difference here in the arrays. So swap version 3a didn't work. So let's go back to the code. And let's try to figure out exactly what happened. I call my function with a1 and a2. So little stack diagram here to help us understand. This is my stack. I'm pushing on the stack the address of a1 index 0. This is what a1 represents, right? Then the address of a2 index 0. I don't have to push the size since I just want to swap around those address values. So what happened next? Inside of my function, this is it, swap array 3a. I have a local variable tmp of type pointer on int. So let me complete my stack diagram. This would be P1, this would be P2, this would be TMP. TMP is also a pointer, so contains an address. Which address does it contain? Well, let me go back to the code. Right now, nothing. Then on line 78, I assign TMP to P1. So here's what's happening there. TMP is assigned the content of P1, which is address of A1 index 0. Alright, so P1 was pointing actually to the first element of array A1 in the main. TMP is now pointing to the same first element of array A1 in the main. If I represent my array A1 here in the main, not on the stack, but using a graphical diagram like this, an array A2, what I have right now is this guy points to the first element, so does this guy. Let's go back to the code. P1 is assigned P2, line 79. Okay, so now P1 is overwritten. Okay, a couple of difficulty here erasing anything at all apparently. Okay, P1 is overwritten by the content of P2, which means pretty much we have now in P1 address of A2 0. So this row no longer makes sense. Okay, I need to remove it. Now P1 is pointing to, clean up this mess first, is pointing to A2 index 0. There we go. What happened next? Line 80, P2 is assigned TMP. Let's go back to the stack diagram, and this is actually how you trace and understand code. Okay, so P2 is assigned whatever is in TMP, which is the address of A1 index 0, thus making P2 point to this guy here. So we did our swap, right? P1 is now pointing to the beginning of A2. P2 is pointing to the beginning of A1. So we did the job. And then we return from the function. What happened when I return from the function? Everything that is on the stack is going to be wiped out. So TMP is a local variable for my function. Wiped out. Let me switch to an eraser that is a little bigger here, otherwise this is going to take us forever. So TMP is actually wiped from the stack. P2 is a parameter, same thing, wiped from the stack. P1 is also wiped from the stack. So all the modification I did on the activation record of my call to the function, which means that when the function terminates, nothing is there anymore. So that explains why it's not working. You can view it empirically by testing the program. The stack diagram is actually explaining to you exactly why it didn't work. This problem that we just went over is not new. We had exactly the same problem in the textbook when trying to swap two integer variables from within a function. This is the old problem of passing things by value as opposed to passing things by reference. But wait a minute, I passed here pointers, right? So I passed by reference. Well, not exactly. What you wanted to modify were A1 and A2. You didn't pass the address of A1 and A2 from the main, so why would you expect that it would work? Actually, this is even more complicated than that. So we're going to leave this thought in suspension for a couple of minutes, okay? And we'll come back onto that. Right now, let's try to do the best we can to understand everything about those array notation and their equivalence with pointer notation. Let's try another version of our function, swap array 3b. Same code, same exact code, but I'm trying here to change my declaration of P1 and P2 from pointers to this empty array parameter notation. Well, first question, does it compile even? Okay, we are still working on clarifying here how we can interchange those two notations. So I have here the version 3a, which I think I just realized it's maybe like, yes, it is inversed compared to what is in the exercise, but that's okay. 3a is 3b in your exercise sheet, and 3b is 3a. Okay, we have them both, sorry, in our code. So we are going to try to compile again. and they should be raising absolutely no error. So that's fine. It raises no error because we are using this notation again as a substitute of the pointer notation in the context of passing array parameters. So does this compile? Yeah. Now, there is one more thing here. Unlike the previous version, where we actually only used P1 and P2 with their empty square bracket notation to access element, now we are assigning things to P1 and P2. So we are assigning to something that has been declared pretty much as an empty array the value of another address. This is only possible when dealing with arrays. If you try to assign something to A1 and A2, for example, in the main, this will not work. It is only acceptable here because of the strong equivalence between P1 and P2 being declared as empty arrays here parameters, and P1, P2 being declared as pointers. This is the only reason for which this is working. So this is pretty much what this is guiding you through. The rest of the exercise is asking you to make a little test. What if I have in my main int another 3 and an int star p? I assign another to p. We saw that this is perfectly legit. What about assigning p to another? From a logic perspective, we are not breaking anything, but we are actually conflicting with the way our language is handling data type. So once again, we're going to try to establish the difference between what you can do with array parameters and what you can do with arrays defined as local variable or global variable. Let's go back to the code real quick. Let's go to our main, and we're going to test this real fast. Here we go. Let me go here and declare an array another of size 3. Then let's get a pointer p. P equal another inside p. Let me save this file. Let's try to compile it again. Incompatible type in assignment, line 31. I'll go back to the code, line 31, incompatible types in assignment. So that shows you that outside of the context of parameters, an array, a full-fledged defined array like another, is not considered to be the same thing as a pointer on int. Okay? You can also understand this visually. Let me try to represent to you what happened when you declare int another and int star p in the main. When you declare int another in the main, the name another is pretty much an alias. Every time you talk about another, you talk about this array of 3 elements. Like we already said, this name is strictly equivalent to address of another index 0. This is the address of the first element of the array. When you declare p as a pointer on int, you have a variable p, which is only 4 bytes. Okay? Another corresponds to an array of 4 bytes, 4 bytes, 4 bytes, that is 12 bytes, enough to host 3 integers. P, on the other hand, is a variable that is just 4 bytes, only meant to contain an address. When you make P point to another by writing P is assigned another, you have the following situation. P is now a variable on its own that points to another. Another, the name another, on the other hand, is not a pointer to the array. The name another itself is understood by our language as meaning the address of the first element. So there is one less indirection. Trying to access an array through a pointer means that you have a pointer existing somewhere in memory containing the address of the first element of the array. When you define an array with a name, this name itself corresponds to the address of the first element of the array. So there is a little difference, a subtle difference, but a difference that doesn't escape the compiler when you try to misuse actually this notation. So what is the output of the compiler on this code? You can cut and paste what you obtain from your terminal. What are the implications on whether C allows us to assign a value to an array variable? It doesn't. Clearly doesn't. Once again, the only situation in which this is different is when you pass an array. So the parameter notation for an array differs from the local or global variable situation. So let me put back the code here. We are going to actually clean this, and then we are going to move to the next step of this exercise.